Okay, so we are on our second video for work and energy. So we're going to call this work and energy part 2. Where part 1, we dealt with energy in general, and we looked at some of the ways that we store energy. Well, now we're going to shift gears and we're going to talk about not stored energy, but energy that's doing something for us. So we are going to talk about kinetic energy. And kinetic energy is energy due to the motion of an object, right? When we get something moving, it now has the ability to apply a force and make something else move. It now has energy that can do work for us, right? And if we go back to the two that we talked about last time, gravitational potential energy. Oh, there we go, gravitational potential energy. Well, if we let something go, it'll fall, which means it'll start moving. And because it's moving, it now has the ability to hit something and make something else move. Same thing with spring potential energy, whether it's the spring itself or something we launch from the spring. Excuse me, right? If we let it go, it now has the ability to apply a force to something else and make something else move because we're letting it move. So kinetic energy has to do with motion. Oh, that's the wrong side, sorry. Has to do with motion, energy due to the motion of an object, right? And it's because something's moving, it has kinetic energy. So going back to looking at equations, and I'm not sure I have the order like that, but we're going to do the equation first before the example. Kinetic energy and kinetic energy equals. So let's think about it. Let's say we have a bowling ball and I throw a bowling ball so it's moving down the lane, right? And it hits the pins and I'm like, ooh, I really wish I had more energy so it did more work on these pins. Well, one of the things I can do is I can get the bowling ball going faster. Now, there's many different ways to make it go faster. I could throw it harder. I can let it like roll down a ramp first. So there's different ways to increase the speed. But in the end, how fast the bowling ball matters. And it's not just speed, it's speed squared. So the speed of the object definitely matters because it has to do with the motion, right? And this becomes important when we think about it in real life situations, again, because it's speed squared. If I'm in a car accident at a certain speed, I will have done a certain amount of work or damage. If I get into the same type of accident, I'm going twice the speed, I do 4 times the damage. I go 3 times the speed, I do 9 times the damage, right? So, driving real fast, the implications of that are bigger and bigger when we're looking at it through, the physics lens, right? If you get into an accident going 30 miles per hour, that's something. You get into the same accident going 60, you do 4 times the damage. And if you're going 90, you do 9 times the damage, right? So as our speed goes up, our ability to do damage goes up parabolically. All right, but going back to just looking at this equation, the speed of the object definitely matters. The other thing that matters is how big is the object, right? If I'm throwing a bowling ball and I'm not happy with how hard it's hitting the pins, well, one thing I could do is get a bigger bowling ball, right? Get one that's more massive. So the mass definitely matters. And those are the only 2 things that matter. So kinetic energy is 1/2 the mass times speed squared. And so let's just take this and move it down to the equation. There we go. And what are types of kinetic energy? And maybe that was a better word than example. What are types of kinetic energy? Well, the first type of mechanical energy is the first type of kinetic energy is mechanical energy. Mechanical. There we go. And I even fixed the spelling there. So the first type of kinetic energy is mechanical energy, which is objects that we could see moving around that can hit other things, a car, a ball, a person, right? So again, this would be our third type of mechanical energy, which is mechanical kinetic energy, which tends to be things that we could see moving around, right? We could lump them all into one group, and if we just know the mass of that object that's moving and how fast that object's moving, we can calculate its kinetic energy. On other scales where we can't see it, well, certainly there can be some electrical kinetic energy. If we get charges moving around, then they tend to strike other things and do work on those other things, which could be felt in terms of heat or light or something like that. So that certainly can be one. Light, just to say it, right? Light is a form of mechanical kinetic energy, right? These photons are moving through the air. When they strike our eyes, they do work, which allows us to see. When they hit us and we feel warmth, and then that's because they have kinetic energy, right? So there's lots of them. Sound would be another example. So we have a few different types of kinetic energy, right? But then what does it matter how much energy these things have? Well, it has to do with how massive the objects are. It has to do with how fast those objects are moving, right? And that determines how much work they're going to do or how much energy's been passed on. Because again, when you do work, you change an object's energy. So when we have something with kinetic energy and it does work on something else, that means it's going to give some of its energy away and something else is going to get that energy. So here are some types of kinetic energy. And again, in this section, we're going to focus on the mechanical energy, which tends to use this equation. Now, knowing different types of energy and calculating different types of energy is somewhat useful in itself, but really the main concern is when we deal with this stuff, we are talking about conservation of energy, or we're looking at all the different types of energy an object has so we can see what it can do later. And none of this would be possible without this understanding of conservation of energy. And conservation of energy tells us energy cannot be created nor destroyed, only altered in form. We can't make energy out of nothing, and energy can't just disappear. What it can do is change from one type of energy to another. We take a rock and we hold it up in the air, it has gravitational potential energy. We let it go, well, it's going to lose that gravitational potential energy, but it just doesn't go away. That's going to turn into kinetic mechanical energy or kinetic energy, right? As it's falling, it's picking up speed. So as the gravitational potential energy goes down, here at the top, it has gravitational potential energy because it has a height, it has a mass, right? And then as it's falling, sure, it still has some gravitational potential energy because it still has a height, but it has less because the height went down. So it also has kinetic energy because it's picking up speed. And then right before the ground, well, the gravitational potential energy is zero because the height's essential is zero. So then it just has kinetic energy because it's going real fast. And then it hits the ground. Well, that energy didn't just disappear. It turned into other forms. It turned into some sound. We probably heard it hit the ground. It turned into some heat. If we touch the ground, it's probably warm there. Could very well have turned into some work on the ground. And we see that now there's a dent in the ground, right? So it turned into some different things, right? So conservation of energy becomes very important because it's telling us, hey, when we have a certain amount of energy, it doesn't just go away, it does things for us, right? And this is the foundation of so many different things in physics, certainly, but also in engineering and in our environment, right? We do things and they have an effect and they simply don't go away, right? We have a certain amount of energy that comes into the earth. And if we create energy and we don't allow some of the energy to leave, then our earth is gaining more and more and more energy, which is global warming, right? So there's lots of implications of this conservation of energy, right? And on the flip side, right, we can't make energy from nothing. So power plants, they don't make energy from nothing, right? They provide us all this electricity that we use all the time. Well, they didn't make this energy. They had to find sources of energy and turn it into electrical energy for us. It had to come from somewhere, right? So we had to burn fossil fuels. We had to take it from sunlight. We had to go through a nuclear reaction, which released it from the nucleus of an atom, right? But we think about power plants, it's not magic. They're not making it, they're not making energy for us. They have a large source of energy and they are changing it into electrical energy for us, right? And no matter which one we're using, there's some consequences for that, right? Because we're changing one thing into another. So that's conservation, right? It works both ways. When we have things with high energy, that energy doesn't go away. It has to turn into other types. And then if we're trying to make a lot of energy, well, then that means we have to find a place that already has a lot of energy in there and we could turn it into what we want. Now, using just the equations, and this equation can get, this overall equation for conservation of energy can get huge depending on what we're talking about, but we're just going to stick with the mechanical energies for right now. So what we're saying is, let's say we look at a situation and we want to find out how much energy it has. Well, then we can certainly calculate its gravitational potential energy. If there's a spring involved, we can calculate its spring potential energy. So this is the gravitational potential energy it has initially. Then we have the spring potential energy that it has initially, and maybe it's moving. So then we look at how much kinetic energy it has initially. And the only other energy we care about is the energy through work, is something doing work on it. Because if you do work on something, you are giving it some of your energy. So I'm going to call this not the work initial, but the work in. How much work are we planning on doing this object? So how much energy do we plan on giving it? Now, all that together, that is going to equal a total energy. And while each type of energy can change, this number is constant. And again, not that I want to, keep beating this point, but yeah, we could add other energies into this, right? We could add tons of other energies, where you had another 4 more potentials, we had another 3 more kinetics, and they all in the real world are part of this. But let's keep this equation somewhat simple, and let's just deal with situations where the mechanical energy is what's changing, instead of bringing in other forms of energy. So this total energy stays constant, but certainly types of energy can change in there, right? Maybe, right, there's a different amount of gravitational potential energy, spring potential energy, kinetic energy, and maybe some energy leaves the system. And if it leaves the system, well, then that means this object did work on something else. So these values, these final values, they still have to add up to the same total energy. The total energy stays the same, but it's quite possible that maybe the gravitational potential energy went down because we dropped something. So maybe there's less of this, which means somewhere else something had to go up. Maybe it's the kinetic energy, maybe it's the work, right? Point being, right, they have to add up to the same number, but they don't have to be the same amounts. Within the 4 things on this equation, if one goes down, something has to go up. And if something went up, something else had to go down, because they still have to add up to the same total. That is the conservation of energy. All right, so in the next video, we will look at some examples of really conservation of energy. We can calculate individual things, and then we will look at how they work as a group in this law of conservation of energy. And we'll calculate a kinetic energy situation too, certainly.